Hello and welcome back to the deep dive. I'm your host, the tech builder here, usually the one, trying to figure out how the gears actually turn under the hood.
And I'm your expert, the big picture explainer,
Mm.
here to figure out what it all means for the rest of us.
Yeah, and we spend a massive amount of time on this show looking at the shiny stuff, the implications, the future of work.
The ethics of automation, yeah.
Right, exactly. We're usually looking 5, maybe 10 years down the road. But in doing the research for this deep dive, we realized we skipped a step.
A pretty big step, honestly.
Yeah. I mean, we talk about AI constantly. It's the buzzword of the century right now. But if I put you on the spot today, and I promise I'm not going to, so don't panic, but if I asked you to explain the difference between, say, a parameter and a token without looking at your notes, could you do it?
Before digging into this massive stack of research, absolutely not. And I think that's the boat most people are in. AI has totally permeated our phones, our cars, our email inboxes. But the vocabulary, it is still stuck in the engineering labs at MIT or Stanford.
Totally.
You hear words like hallucinations, transformers, embeddings thrown around in boardrooms now, and half the room is they're just nodding along, hoping nobody calls on them to explain it.
It's the emperor's new code. We're all just nodding to avoid looking like we're behind the curve. So for you listening, today we are doing something a bit different. We are going back to basics, but like extreme basics.
Mm-hmm.
We are going to build a mental AI glossary from the absolute ground up.
Think of this as a mission. We want to make these concepts click for a smart eighth grader with a curious mind, but with enough technical meat on the bone that even a seasoned tech professional might say, I never actually thought about it that way before.
We have a roadmap for this deep dive. We're going to start at the 30,000-foot view, the big, messy concepts like AI versus machine learning. Then we're going to zoom in on the infrastructure, like how these machines actually learn.
All right, the foundations.
Then we'll look at the engine powering the current boom, the big models of the world. And finally, we'll get into the microscopic quirks, the bugs, the knobs, the weird stuff that makes it all work.
It's going to be a journey from a continent down to a single grain of sand.
I love that image. So let's start with that continent, the first term on our list, the biggest wrapper of them all, artificial intelligence.
Right. And this is where the confusion starts immediately, because AI has basically become a marketing term.
Oh, yeah. You see it on toaster ovens now.
Exactly. AI-powered toasting technology.
Which is absurd.
It is. But technically, historically, AI is a catch-all. It is a field of computer science focused on creating systems capable of performing tasks that normally require human intelligence.
Human intelligence being the key variable there. So we're talking reasoning, learning, perception, understanding language.
Solving puzzles, all of that. And the analogy that really helped me visualize this relationship between all these different terms is geography. I want you to think of AI not as a specific technology, but as the entire continent of North America.
Okay, North America, huge place, very diverse.
Massive. It's a landmass. And inside that landmass, you have different countries, different climates, different terrains. When someone says, I work in AI, it's like saying, I live in North America.
Right, which could mean anything.
Exactly. They could be in Toronto, they could be in Mexico City, a cabin in Alaska, or a beach in Miami.
So under this North America definition of AI, you have things that are actually pretty old school. We aren't just talking about the advanced chatbots of today.
No, not at all. Think about a robot from the 1980s that could navigate a room without bumping into a chair. That is AI.
Right, or that chess program from the 90s.
Deep Blue, the one that beat the Grandmaster, that is AI. The system that has been recommending movies to you on streaming services for the last 10 years, also AI. They are all residents of this continent, even though they do wildly different things and operate on entirely different principles.
It's interesting because back in the day, we used to call the old stuff good old-fashioned AI or Joe F AI.
Right, Joe F AI.
It was symbolic, it was logic-based, it was essentially a bunch of if-then statements written by human engineers.
If the king is here, move the pawn there. That's still AI, but it's brittle. It's like a very rigid city spreadsheet. But the landscape changed. And that brings us to the next layer down on our map, the country inside the continent.
Topic number 2, machine learning, or ML. Now, this is where people get tripped up constantly.
Up all the time.
They use AI and ML interchangeably. They'll say, oh, we're using AI when they actually mean ML, or vice versa.
You do, and they really shouldn't. If AI is the continent of North America, machine learning is the United States.
Okay, so it's a dominant superpower within the continent. It takes up a huge amount of space and drives the economy. But it is a subset.
Correct. And here's the fundamental shift. This is the moment where the timeline basically splits. Traditional programming, the old way of doing things we just talked about, was about giving the computer a rule book.
Right.
You, the human, had to be the smart one. You had to figure out every possible scenario and write a strict rule for it. If X happens, do Y.
Which works fine for a calculator,
Hmm.
or maybe for a tax program where the rules are completely fixed and predictable. But it's terrible for, say, recognizing a picture of a cat.
Exactly. You can't write a rule for every possible angle of a cat's ear or every different lighting condition in a living room.
You'd have millions of rules and it still wouldn't work. The cat turns its head and the system breaks.
Right. So machine learning flips the script entirely. Instead of giving the computer the rule book, you give it the data. You show it the answers and you say, you figure out the rules.
This is the massive shift from rules to patterns.
Precisely. The classic example, and I think the one that makes it click for everyone, is the spam filter in your email. In the old days, pre-ML, you might try to program a filter that says, if the subject line contains the word prize, and click here, block it.
But spammers are smart. They realize what you're doing, so they change prize to reward. They change click here to visit now, and suddenly your rule book is completely useless.
You're just playing whack-a-mole at that point, constantly updating your code manually.
Right. So with machine learning, you don't program block the specific word.
No, you take a massive data set, thousands of emails that real users have marked as spam, and thousands that users have marked as safe, and you feed them all to the machine.
And the machine looks at them statistically. It notices things a human might completely miss. It notices, hey, 99% of the time when the sender address has 4 random numbers and the body text is in all caps, the user deletes it.
Exactly. It writes its own rule book based purely on probability. It learns to associate certain complex patterns with the concept of spam. And the beauty of this is, if the spammers change their tactics,
Which they will.
the machine just needs to see a few new examples of the new tactic to update its internal rulebook. You don't have to rewrite a single line of code. You just feed it fresh data.
So the computer is effectively writing its own software.
In a sense, yes, the computer is determining the logic.
Okay, so we have the continent, which is AI, and the country, which is machine learning. But machine learning is still a broad category. There are simple ways to do it, like linear regression, just drawing a line through a graph of data points. But that's not what's driving self-driving cars or modern language models.
No, not at all. To get to the really advanced stuff, we need to talk about the infrastructure. How is the brain of the AI actually built? And that brings us to our third topic, neural networks.
Now, this is a term that sounds incredibly sci-fi. It sounds like something straight out of the Terminator. But it's actually rooted in 1950s biology, isn't it?
It is. It's inspired by the biological neural networks in animal brains. But I actually want to steer away from the biological brain analogy for a second, because it can get really misleading. We tend to anthropomorphize it way too much. We start thinking the computer is thinking like us.
Okay, so it's not a brain. What are we building? What's a better visual?
Let's use a massive city subway system.
Listening a subway system.
A neural network is a collection of connected nodes. We call them artificial neurons. In our analogy, these are the subway stations and the connections between them. Those are the train tracks.
Okay, so information, the data hops on a train at the first station.
Right. Let's say the data is a single pixel from a photograph. It enters the station. The station does a little bit of math on it, basically processing the passenger, and sends it down the tracks to the next station. But here is the magic part. The network has something called weights.
Weights. This is a crucial concept to grasp.
Think of weights as the quality and capacity of the train tracks themselves. Some tracks are high-speed rail, super strong connection, very important route. Some are rusty old tracks that barely get used or are very slow. When the network is in the process of learning, it isn't growing new neurons or building new stations. It's adjusting the tracks.
So if a certain path between stations leads to the right answer, like correctly identifying a cat in that picture, the system says, hey, that was a really good route. That specific combination of stations got us the right result. And it upgrades that track.
It makes the connection stronger.
It gives it a higher weight.
Exactly. It essentially widens the tunnel. And if a route leads to the wrong answer, like confidently saying a dog is a cat, it downgrades the track. It says, don't go that way next time. Maybe it closes it off entirely. It's a constant iterative process of traffic control.
The example that always helps me visualize this layering process is facial recognition, because it doesn't just happen all at once, does it? It's not like one single station sees a whole face.
No, it's hierarchical. Imagine the subway system processing a photo of your friend. The first layer of stations, the first neurons, They're very, very simple. They might just detect raw edges. Here is a vertical line of contrast. Here is a horizontal curve. That's it. That is all they know.
They pass that extremely simple info down the tracks.
To the next layer. And that layer combines those edges. It says, hey, if I put two vertical lines and a curve together, I get an eye shape. And then the next layer down the line says, well, if I have two eyes and a nose shape, I have a face.
So as you go deeper and deeper into the subway system, the concepts get progressively more complex and more abstract.
Which leads us perfectly to the next term.
Yeah.
The one that totally dominates the headlines, deep learning.
Right. Because usually when we hear about neural networks now, we just hear the phrase deep learning. Is that just a rebranding? Is it just marketing spin?
Not exactly.
Yeah.
Go back to our geography map for a second. If machine learning is the United States, deep learning is New York City.
It's dense. It's vertical.
It's incredibly complex. The key word there is deep. That refers to the layers. We aren't just talking about a neural network with an input layer, a middle layer, and output like a flat, sprawling town. We're talking about networks with hundreds or even thousands of layers.
Skyscrapers, subways stacked on top of subways, fiber optics running on top of sewer lines.
Yes. The deep in deep learning essentially just means many hidden layers. And this depth is what allows for the incredible nuance we see today. A simple neural network can recognize a handwritten number on an envelope, like a 7. A deep learning network can recognize a pedestrian stepping off a curb in the rain while wearing a dark coat at night.
Because it has enough layers to process that level of chaotic, real-world detail?
Exactly. It creates a representation of the world that is incredibly rich, simply by stacking these very simple math operations on top of each other millions of times. That's what powers self-driving cars.
So just to recap the foundation before we move on, we have the continent, which is AI, the broad idea. We have the country, machine learning, which is the method of learning from data, not rules. We have the subway system, neural networks, which is the infrastructure. And we have the dense city, deep learning, which is the massive, layered version of that infrastructure.
That's the what. But I really want to talk about the how. Because a subway system without a schedule is just total chaos. You have to actually teach it how to run.
Right. We need to talk about learning styles. How does the machine actually adjust those weights on the tracks? There are 3 main ways, and they map surprisingly well to how humans learn.
They really do. So this brings us to part 2 of our glossary, the learning styles.
First up on the docket, supervised learning.
This is the most common form, historically speaking. The analogy here is the classroom with a teacher.
And the teacher is holding the answer key.
Yes. Imagine you're back in kindergarten.
Yeah.
Teacher holds up a flashcard of an apple and says, apple. You say apple. She holds up a banana and says, banana.
The data is labeled. That's the technical term, right?
Correct. The training data has strict labels attached to it. This image is a cat. This audio recording is the word hello. This email is spam. The model looks at the data, makes a guess, and the teacher, which is just the algorithm comparing the guess to the label, corrects it instantly. No, that's not a cat, that's a dog. Adjust your weights.
This is exactly why companies like Scale AI exist, right? They literally have armies of humans sitting at computers drawing boxes around stop signs and photos. They are manually creating the answer key for the supervised learning process.
Exactly. It's very labor intensive. It requires humans to do a ton of upfront work, but it's highly accurate for specific tasks. If you want a reliable spam filter, you use supervised learning. You tell it very clearly what spam looks like.
Okay, but what if there is no teacher? What if you just dump the data on the table and say, good luck? That's the next type, unsupervised learning.
This is where it gets a little mysterious and really fascinating. Imagine a child given a giant bin of Lego bricks. But there are no instructions. There's no picture on the front of the box. And there is no teacher in the room to tell them what they're supposed to build.
Just a chaotic pile of plastic pieces.
Just raw, unlabeled data. But the human brain and the AI naturally looks for patterns. So even without instructions, the child just starts organizing. Maybe they put all the red ones together in a pile. Maybe they separate the tiny single pieces from the big blocks.
Or maybe they notice that the wheels always seem to go with the axles, so they group those together.
Precisely. They're discovering the structure that is intrinsic to the data itself. The machine finds hidden patterns or clusters without anyone telling it what to look for.
The famous business school example here is the beer and diapers story.
Oh, the classic data mining legend.
Right. The story goes that a retailer fed their massive sales data into an unsupervised learning algorithm. They just said, find patterns. They didn't tell it what to look for at all. And the machine came back and essentially said, hey, did you know that on Friday afternoons, There is a statistically significant group of people who buy diapers and beer at the exact same time.
A pattern literally no human manager would have thought to look for. Because why would diapers and beer go together?
Right. The working theory being dad's picking up supplies for the weekend, I have to watch the kid, I'm grabbing a six-pack.
Whether this story is perfectly true or just a fable, the principle is entirely sound. Unsupervised learning finds the signal in the noise that you didn't even know existed. It's used heavily in recommendation engines, like people who listen to this song also listen to this totally obscure track and in cybersecurity, spotting weird network activity that just doesn't fit the normal pattern of the company.
It's the engine of discovery.
It really is.
Okay, the third style is my personal favorite because it feels the most alive to me. Reinforcement learning.
The analogy here is very simple. It's training a dog.
No answer T, no sorting Legos. It's all about consequences.
It is trial and error. When you teach a dog to sit, you don't explain the geometry of sitting to the dog. You don't show it a diagram of a canine skeleton. You just say, sit. The dog looks at you. Maybe it barks. Nothing happens. Maybe it spins in a circle. Nothing happens.
But eventually, just by random chance, its butt hits the floor.
And boom, Crete. Positive reinforcement. The dog's brain instantly wires that connection butt on floor equals yummy snack.
And if it bites the sofa, bad dog. Negative reinforcement.
In AI, we call the snack the reward function. The AI is an agent placed in an environment, and its only goal, literally its entire reason for existing, is to maximize its score, to get as many treats as possible. The most famous example of this, by far, is AlphaGo.
The system that beat Lee Sedol, the world champion, at the game of Go.
Go is a game with more possible board configurations than there are atoms in the observable universe. You simply can't program rules for it like you can with chess. It requires intuition.
So how did they train it if they couldn't give it rules?
They had it play against itself. Millions and millions of times. A win was a treat. A loss was a punishment. Over time, it figured out strategies that humans hadn't discovered in 2,500 years of playing the game.
There was that famous move 37.
Yes. In the second game against the world champion, the AI made a move that confused everyone in the room. The commentators were completely baffled. They honestly thought it was a glitch or a mistake. They said, no human would ever play that move. It looks weak.
But it turned out to be the absolute turning point of the game.
Exactly. The AI played it because in its millions of simulations, it learned that this weird, counterintuitive move increased its probability of winning by a tiny margin. It didn't care about human tradition. It didn't care about style. It only cared about the reward.
That is the power of reinforcement learning. It can actually surpass human imitation and find completely new solutions that we wouldn't even think of.
It completely breaks the ceiling of human knowledge.
Okay, let's shift gears. We've covered the basics of how machines learn, but we need to talk about the specific technology that is blowing everyone's minds right now. The tech behind ChatGPT, Claude, Gemini. We need to talk about the modern AI engine.
This is part 3. This is where we enter the era of generative AI. Yeah. And the core of this whole boom is the LLM, the large language model.
We hear this acronym constantly, LLM, but let's actually break it down. What actually is it?
The technical definition is that it's a type of deep learning model trained on a massive amount of text data to predict the next word in a sequence. But that sounds incredibly dry and doesn't really capture the magic.
Let's use the librarian analogy.
Think of an LLM as a librarian. But not just any librarian. This is a librarian who has literally read every single book in existence. Every website, every Reddit thread, every scientific paper, every poem, every novel ever digitized.
That is a staggering amount of reading.
It is. And because this librarian has read everything, they know exactly how words fit together. They know the statistical likelihood of what word comes after another. If I say, pour peanut butter, and the librarian knows there is a 99% chance the next word is jelly.
But, and this is the crucial philosophical point for you listening, does the librarian actually know what a sandwich is?
That's the nuance.
Yeah.
The librarian has no mouth. They've never tasted a sandwich. They don't know the concept of taste. They don't have a stomach. But they've read a million descriptions of sandwiches. So if you ask them, describe the taste of peanut butter, they can give you a beautiful, highly accurate description.
Not because they experienced it, but because they are synthesizing the patterns of how humans describe it.
Exactly. It is a statistical engine of meaning. It's predicting the conversation based on all the conversations it has ever read.
Now, what makes these modern LLMs so much better than the chatbots we had, say, 10 years ago. I remember talking to customer service bots in 2015, and they were just painful. They got stuck in loops. They didn't understand context at all. If you said the word it, they didn't know what it referred to from the previous sentence, what actually changed.
What changed was the architecture itself, a specific breakthrough called transformers.
This was introduced by Google researchers in that famous 2017 paper, Attention is All You Need.
A genuinely great title, by the way. Before transformers, AI read text exactly like we do sequentially, word by word, left to right. The cat sat on the mat.
And the problem with that is memory, right?
Right. If the sentence was very long, say a full paragraph long, by the time the AI got to the very end, it might have completely forgotten what the subject was at the beginning. It struggled terribly with long-term dependency. It's a bit like listening to a toddler tell a story. By the time they get to the end, they forgot how it started.
So how do transformers solve this? How do they read?
Transformers changed everything because they don't read sequentially. They use an attention mechanism to look at the entire sentence or even the entire page all at once.
All at the same time.
Simultaneously. Parallel processing. The analogy I like to use is the cocktail party effect.
Okay, explain that one.
Imagine you are at a really loud party. There is noise everywhere, people chatting, music playing, glasses clinking. But someone all the way across the room says your name. You instantly focus on that. Your brain filters out the noise and attends to that specific signal. You draw a direct connection between you and that voice.
Okay, that makes sense.
The transformer does this for every single word in a prompt. When it looks at the word bank in a sentence, it instantly attends to every other word to figure out the exact context. If the other words are river and water, it knows bank means the side of a river. If the other words are money and deposit, it knows bank means a financial institution.
And it does this for every word, creating a massive interconnected web of relationships instantly.
Yes. It weighs the importance of different parts of the input data relative to each other. This is what allows it to hold a conversation with you for 20 minutes and still remember something you said at the very beginning. It hasn't forgotten because it's looking at the whole conversation history as a single, massive map of meaning.
That is the secret sauce right there. That's why ChatGPT feels like it's actually listening to you.
It's just paying incredible attention.
Now, inside this transformer brain, there are settings. We call these parameters. When GPT-3 and GPT-4 came out, people were obsessed with the parameter count. Is it 1 trillion parameters? Why does this specific number matter so much?
Parameters are basically the memory of the model. But I prefer the mixing board analogy to explain it.
I love this one.
Imagine a giant sound mixing board in a high-end recording studio. You know, they have those sliders and knobs, bass, treble, volume, fade.
Sure.
Now imagine a mixing board with not just 100 knobs, but billions of them.
Billions of knobs.
Billions. When we are training an AI model, we aren't writing code in the traditional sense. We are basically a sound engineer tweaking those billions of knobs until the output sounds absolutely perfect.
So you feed it data, the output is a little off, maybe it confuses there, so the math tweaks 1 million knobs slightly to the left. You feed it more data, it gets a bit better, you tweak another 1 million knobs to the right.
Exactly. Each knob's final position, its numerical weight, represents a tiny learned piece of information. One single knob might represent a minute rule of grammar. Another group of knobs might represent the historical concept of the French Revolution.
And just to give people a real sense of scale here, GPT-3, the one that really kicked off this whole craze, had 175 billion parameters.
175 billion individual knobs. And every single time you ask it a question, every time you type a prompt, the signal runs through all those knobs to generate the final answer. That is exactly why these models are so incredibly expensive to run. You are powering a machine with billions of active parts for every single query.
It's a computational beast.
It really is.
Okay, so we have the model. We have the librarian with the transformer brain and 175 billion knobs set just right. But here is the problem for businesses and for users like us. The librarian is a generalist. It knows a little bit about everything, but it doesn't know my company's secrets. It doesn't know my internal HR policy. It doesn't know my specific coding style.
Right. The librarian has read the public internet. It definitely hasn't read your private emails.
So how do we fix that? This brings us to part 4, customization. There is a huge debate in the tech world right now about the best way to make AI smart about highly specific topics. Do you use fine-tuning or do you use RAGger?
This is the million-dollar question for enterprise right now. Let's break down the difference using the doctor analogy because this really helped me clarify the cost-benefit analysis.
Okay, lay it out.
Let's say your base model, your GPT-4 or your Claude, is a brilliant general practitioner. It went to med school, it knows biology, it can diagnose a cold, it knows human anatomy inside and out.
But you want it to be a world-class expert in a very rare tropical disease that only affects people in a highly specific region.
Right. So option A is fine-tuning.
Okay.
Fine-tuning is like sending that doctor back to school. You take the model and you train it further on a highly specific data set of tropical diseases. You force it to study. You actively update its parameters.
You are physically changing the brain. You are moving the knobs on the mixing board again.
Yes. The knowledge becomes deeply ingrained in the model. The doctor knows the disease by heart now. They can answer questions about it in their sleep.
That sounds great. Why wouldn't a company always just do that?
Two big reasons. One, it's expensive and slow. Retraining a model takes massive computing power. Two, something called catastrophic forgetting.
That sounds ominous.
It is. Sometimes when you force the doctor to learn so much about tropical diseases, they actually forget how to treat a common cold. You over-optimize the brain and accidentally overwrote old, fundamental knowledge.
Like the brilliant scholar who knows everything about ancient history, but forgets how to tie their own shoes.
Exactly. Plus, if new medical research comes out next week, your fine-tuned doctor is now outdated. You have to send them back to school all over again.
Okay, so what is option B? RAG, Retrieval Augmented Generation.
This is the current darling of the industry. In this scenario, you don't send the doctor back to school at all. You keep the general practitioner exactly as they are, but you give them a really expensive, completely up-to-date textbook on tropical diseases, and you put it right on their desk.
So the specialized knowledge isn't in their head, it's in the book.
Right. When a patient comes in asking about the rare disease, the doctor says, hold on one second. They open the book, look up the specific symptoms, that's the retrieval part, and then they use their general medical training to explain the answer clearly to the patient. That's the generation part.
That makes so much sense. It's essentially an open book test.
Precisely. And for businesses, this is huge. If you want an AI to answer questions about your HR policy, you don't retrain the AI's brain. You just upload the PDF to the textbook pile.
And if the policy changes next week?
You just swap out the PDF. You replace the book on the desk. You don't have to touch the doctor's brain at all. It's cheaper, it's faster, and usually it's way more accurate because the AI can actually cite its sources. It can say, I found this answer on page 4 of the employee manual.
That citation part is critical for trust. Don't just tell me, show me exactly where you found it.
Exactly.
Now for our guy to work for the doctor to quickly find the right page in a massive book, the computer needs a way to find meaning quickly. It can't just look for exact keywords because sometimes people use totally different words for the exact same thing. This brings us to embeddings.
Embeddings are beautiful math. This is how computers understand meaning geometrically.
Geometrically.
Yes. Computers don't know what love or king actually means. They only know numbers. So we turn words into massive lists of numbers. We call them vectors.
How does that help with meaning, though?
Imagine a giant 3D map of a room.
Oh,
Massive
wow.
cloud of points just floating in the air.
Okay, got the visual.
We are going to plot every single word in the English language on this map. But here is the golden rule. We place words closer together if they have similar meanings.
So over in one corner, let's call it the royal corner, we have the point for king. Standing right next to him is queen. A little further away is prince.
Right. And way over in the completely opposite corner, the food corner, you have apple and banana standing right next to each other.
But apple is very, very far away from car.
Exactly. The physical distance between the points represents the similarity in meaning.
So when I search for something on an internal database,
Let's say you search for how to fix a tap. The computer looks at the map. It sees where fix a tap lives in the cloud. It looks at the immediate neighbors. And sitting right next to it is how to repair a faucet. The actual words are completely different. Fix versus repair, taps versus faucet. But the underlying meaning puts them in the exact same geometric neighborhood.
so the search engine knows to show you results for faucet, even though you specifically type tap?
That is the magic of vector embeddings. It turns human language into spatial geometry. You can actually do math with words. The classic example in the field is if you take the vector for king, subtract the vector for man, and add the vector for woman.
You land exactly on the coordinates for queen.
Isn't that wild? King minus man plus woman equals queen, purely through navigating numbers.
That is genuinely mind-blowing. It really shows that language has a hidden structure we didn't even realize was strictly mathematical.
It really does.
Okay, one more setting on our mixing board before we move on. Temperature. You see this in the API settings if you're a developer, or sometimes in the advanced settings of chatbots. Set temperature to 0.7. What are we actually controlling here? The heat of the servers.
No, though they definitely do get hot. This is the creativity knob. It controls randomness.
Randomness? I thought computers were supposed to be perfectly logical.
Well, LLMs are probabilistic. They predict the likely next word. But sometimes the most likely word is just really boring. If I say, the most likely next word is blue.
So temperature controls how risky or weird the prediction is.
Think of it as a chef. A low temperature, let's say 0.1, is a rigorous, by-the-book pastry chef. They follow the recipe exactly. If the recipe says 100 grams of flour, they use exactly 100 grams.
So the output is highly predictable, consistent.
Yes. If you ask a low-temp model for a historical fact or to extract data from a dense spreadsheet, it'll give you the most statistically probable, safe answer.
And high temperature, like 1.0.
That is the experimental jazz chef, the one who thinks, you know what this soup needs? A handful of cinnamon and some chili flakes.
It takes big risks.
It deliberately picks words that are less probable. Instead of saying the sky is blue, it might say the sky is an azure dream.
Or the sky is a screaming void.
Exactly. High temperature creates poetry, weird jokes, interesting stories, but it also massively increases the risk of total nonsense.
So if I'm building a coding assistant to write Python scripts for my team...
Keep the temperature incredibly low. You do not want creative code. You want correct code.
But if I'm building a brainstorming bot to come up with wild ad slogans...
Crank it up. You want the weird, out-of-the-box ideas.
Got it. One last term in this section, multimodal. We are seeing this more and more with models like GPT-4o and Gemini 1.5.
Multimodal just means many modes. Text is one mode, audio is another, video and images are others.
For a long time, these were completely separate fields. You had computer vision people and NLP language people, and they barely talked to each other.
Right. But multimodal models bring it all together into one brain. The goal is to be more like a human.
Explain that.
Well, you are multimodal. You don't have a totally separate brain for seeing and a separate brain for hearing. If you see a dog barking, your visual cortex and auditory cortex feed into the exact same central understanding. You get the full picture seamlessly.
So a multimodal AI can do that. I can show it a picture of a complex line graph that's vision, and I can ask it verbally, what is the trend here? That's audio and text.
And it processes both modalities in the exact same transformer brain to give you a cohesive answer. It's closing the gap between how we experience the world, which is messy and multisensory, and how the machine understands it.
It's becoming less of a pure calculator and more of an observer.
That's a great way to put it.
All right. We have built this amazing machine. It's a North American librarian with a transformer brain, 175 billion knobs, a map of meaning, and a textbook sitting on the desk. It sounds perfect.
It sounds perfect, but it's not.
It really isn't. In fact, it has some very weird, very specific quirks. We need to talk about the bugs, or as the engineers like to say, the undocumented features.
The things that keep AI safety researchers up at night. This is part 5, the quirks and challenges.
First and most famous of all, hallucination.
This is the big warning label on the box.
Yeah.
Hallucination is when the AI confidently states something as a hard fact, but it's completely made up.
Now, I always argue about the word hallucination. It implies the AI is taking drugs, or that it's actively lying. But lying implies intent to deceive. The AI doesn't have intent.
Correct. It's not lying. It's just failing at prediction. The analogy I love is the unprepared student.
Oh, we all knew this kid in high school.
The student who didn't study for the history test at all, but he is incredibly charismatic and articulate. The teacher asks, what was the primary cause of the War of 1812?
And the student stands up, confidently fixes his tie, and says, the War of 1812 was primarily driven by the socioeconomic tensions regarding the trade of cotton between the Northern Alliance and the Southern French territories.
It sounds amazing. The grammar is flawless, the vocabulary is high level, the tone is perfectly authoritative, but the facts, total nonsense.
He's just stringing words together that sound like a history answer.
Exactly. That is a hallucination. The LLM is predicting the next word that sounds plausible, not the word that is factually true. Because remember, the librarian doesn't actually know history. The librarian only knows which words usually appear near the words War of 1812.
There was a famous example in the notes about the 1952 World Series.
Right. If you asked an early version of a chatbot who won the 1952 World Series, it might confidently tell you, the Brooklyn Dodgers defeated the New York
It
Yankees.
sounds totally plausible. It's a classic rivalry. Those words belong together in a sentence.
But it's factually wrong. The Yankees won. The AI hallucinated the Dodgers winning because those words, Dodgers-Yankees 1952 World Series, often appear together in the training data. It went with the statistical vibe rather than the actual fact.
So the takeaway for users is trust but verify, especially with numbers, citations, and legal cases.
Oh God, the court cases. We've seen real lawyers get in huge trouble for citing cases that ChatGPT just completely invented. State versus Smith, a case that never happened but sounds exactly like it should have.
Another quirk is how the model actually eats text. We assume it reads letters like we do, A, P, P, L, E, but it doesn't. This brings us to tokenization.
This is the digestion process. Computers can't process raw text. They need numbers. So before the AI even sees your sentence, it gets chopped up.
The analogy here is cooking.
Yes. Imagine you're a chef and you get a delivery of whole pumpkins and carrots. You can't just throw them in a panhole. You have to chop them into usable pieces.
Tokenization is the chopping.
It chops sentences into little bits called tokens. Sometimes a token is a whole short word like love. But sometimes, especially for longer or complex words, it chops them into weird parts.
Like thinking might become think in ing.
Right. The sentence, I love AI, might get chopped into 4 distinct tokens. I love AI and the exclamation point. Each of those chunks gets a specific, unique ID number.
And this explains why AI is notoriously bad at simple things like spelling or word games, right?
Yes. If you ask an AI how many letters are in the word strawberry, it often gets it confidently wrong. It might say 2 R's instead of 3.
Why? It's a supercomputer. It knows everything.
Because it doesn't actually see the letters R, R, R. It sees the token ID number for the chunk that makes up strawberry. It sees a single entity. It's like asking a human how many brushstrokes are in that painting. You see the full image, not the individual strokes. The AI sees the token, not the letters.
That is a fascinating limitation. It's a massive blind spot created by its own processing efficiency.
Exactly.
Okay, 2 more technical terms that explain why AI sometimes fails to learn properly. Overfitting.
Overfitting is another classic student error. This is the memorizer.
The student who completely memorizes the answers to the practice test but doesn't actually learn the underlying formulas.
They ace the practice exam. They get 100%. The teacher thinks, wow, this kid is a mathematical genius.
But then they walk into the real exam. The questions are slightly different. The numbers have changed from a 5 to a 7.
And the student fails completely. Because they didn't learn the pattern of how to add, they just memorized the specific examples, like 5 plus 5 equals 10.
In AI, this happens when the model learns the noise instead of the signal.
The classic story, and it's a bit of a carable in the industry, is the AI trained to detect tanks. The military trained an AI to spot enemy tanks in photos. It worked perfectly in the lab, 100% accuracy.
Then they took it out to the field and it completely failed.
It turned out all the photos of tanks in the training data were taken on cloudy days, and all the photos of empty fields were taken on sunny days.
So the AI didn't learn what a tank looked like at all. It learned what a cloudy sky looked like.
It overfitted to the weather. It learned the background, not the object. That is the incredible danger of bad data. The AI will cheat if you let it. It will find the easiest, laziest pattern, even if it's the entirely wrong one.
And finally, let's talk about the archer. Bias and variance.
This is the fundamental trade-off in accuracy. Imagine you are at an archery range trying to hit a bullseye.
Okay, got it.
First, let's talk about high bias. This is also called underfitting. This is the archer who groups their arrows very, very tightly together. They are precise, but they are aiming at the completely wrong spot.
So all the arrows hit the top left corner of the target board.
Right. They are consistently wrong. Their technique is just too simple. They are completely missing the complexity of the wind or the distance. They have a bias towards a wrong assumption.
That's high bias. What is high variance?
High variance is the exact opposite. The arrows are all over the place. One is high, one is low, one is left, one is right.
It's a mess.
It's a mess, but, and here's the math joke, if you average them all out, the center point would actually be the bullseye.
So they are trying way too hard.
They are too sensitive. They are overreacting to every little breeze, every tiny noise. They're changing their aim constantly. That is overfitting. They're capturing way too much noise.
So the goal of any AI engineer is to be the Goldilocks archer. Not too rigid, which is bias, and not too chaotic, which is variance.
Exactly. Finding that delicate balance, the bias-variance trade-off, is the true art of machine learning. It's not just writing code, it's intuition.
Wow. Okay, let's take a breath. That was a lot of information.
We just sprinted through about 70 years of computer science.
But I think the narrative really holds together. We started with the vast continent of AI. We traveled to the country of machine learning. We rode the subway of neural networks into the deep, dense city of deep learning.
We met the teacher for supervised learning, the Lego builder for unsupervised, and the dog trainer for reinforcement.
We introduced the librarian, the LLM, with their transformer brain and 175 billion knobs. We gave them a textbook for ag and a map of meaning with embeddings.
And we warned you about the unprepared student hallucinating answers and the memorizer overfitting to the wrong details.
When you lay it all out like that, it really makes you realize this isn't magic.
That is the most important takeaway for anyone listening. It feels like magic when you use ChatGPT. It feels like there's a soul in the machine. But it's not magic. It's math. It's statistics, patterns, and a lot of tiny adjustments to billions of knobs.
And knowing these terms, having this glossary in your head, it changes how you see the news. When you hear the model is hallucinating, you don't think, oh, it's going crazy. You think, statistical prediction error. The student didn't study the facts.
Or when a company proudly says they are fine-tuning a model, you know they are sending the doctor back to school, which means they're spending a massive amount of money and taking a risk. You can actually ask, hey, why not just use our egg instead?
It gives you power over the technology. It turns you from a passive user into a truly informed observer.
It really does. And I hope for everyone listening that the next time you're in that meeting and someone drops the word transformer, you don't just nod silently. You picture the cocktail party. You picture the attention mechanism working.
I would strongly encourage everyone, if there was a section here that went a bit too fast, go back and listen again. Especially that distinction between fine-tuning and RAG in Part 4. That is going to be the defining business decision of the next few years.
Absolutely. Let these analogies sink in. Visualize the subway. Visualize the librarian. It sticks so much better that way.
Thank you so much for joining us on this deep dive into the glossary of AI. We'll be back next time to probably talk about what happens when the librarian actually gets smarter than us.
Can't wait. Thanks for listening.
See you next time.